Welcome viewers. In this video we'll see the Maxwell's equation. There are four equations available in both integral and differential form. First we'll see the first Maxwell's equation, that is from Ampere's law. First Maxwell's equation is obtained from Ampere's law. So according to Ampere's law, the line integral of magnetic field intensity H around a closed path is equal to current enclosed. It is integral H dot dl equal to I. So that is the statement given by Ampere's law. In general case, we consider the total current involving both conduction current and displacement current. Here we are considering both conduction current and displacement current. Conduction current means current flowing through normal conductor with resistance R and applied voltage V. Displacement current is nothing but current flowing through the capacitor. The current flowing through the capacitor is termed as displacement current. Here we are considering both conduction current as well as displacement current. So integral H dot dl equal to double integral J dot n cap ds, that is equal to I. So integral H dot d equal to I. In terms of current density is given, double integral J dot n cap ds. But J equal to sigma E plus dou d by dou t, the current density in other form. Now we can replace this J with this expression. So integral H dot dl equal to double integral sigma E plus dou d by dou t into n cap dot n cap ds. If the medium is free space, that is, we can replace d equal to epsilon E. Right, the d available here can be replaced as epsilon into E. So that integral H dot dl equal to sigma E plus epsilon dE by dt. d by dt is now replaced with dE by dt into n cap ds. Right, that can be splitted into two. We can split into two terms. Integral H dot dl equal to double integral sigma E dot n cap ds. That is, these two are multiplied. Now these two are multiplied. Epsilon dou E by dou t into n cap ds. Right. So the first term is referred as a conduction current. The second term is referred as a displacement current. You take this is equation number 1. Right. So finally we can write integral H dot dl equal to double integral curl H dot n cap ds. This term can be replaced as curl into H. Right. So this is nothing but the Maxwell's first equation in integral form. Integral H dot dl equal to double integral curl H dot n cap ds is the Maxwell's first equation in a integral form. Now we'll see the differential form. So according to Stokes' theorem, this integral H dot dl can be written as double integral curl H dot n cap ds. Right. So according to Stokes' theorem, it is written like this. We take this equation number 2. So by comparing equation 1 and 2, this left hand side is equal, integral H dot dl. So that we can equate the the terms available in right hand side. So that curl H equal to sigma E plus epsilon dou E by dou t. That is available in equation 1. So this curl H is written as del into H, that is equal to sigma E plus epsilon dE by dt. Right. So this equation is nothing but Maxwell's first equation in differential form. Previous one is the integral form. This is the differential form. Right. So now we got the Maxwell's first equation from Ampere's law, both in integral form as well as differential form. Now we'll go to the second Maxwell's equation. The second equation is from the Faraday's law. What is Faraday's law? Faraday's law states that the voltage induced around a closed path is given by negative of time rate of change of magnetic flux in the path minus dou by dou t of pi, rate of change of flux in a decreasing order. That is given by Faraday's law. EMF equal to minus dou by dou t of pi. Now we'll see the flux density B equal to pi by A. So by cross multiply this, so pi equal to B into A. So that can be written as phi equal to double integral b dot n cap ds. Now we'll replace this pi with this expression. From equation 1, this pi is now replaced with this expression. So the equation 1 become EMF equal to minus dou by dou t of double integral b dot n cap ds. So that it can be written as integral E dot dl. The EMF also expressed in terms of integral is E dot dl. That is equal to, multiply this inside, minus double integral dou b by dou t dot n cap ds. Right? So integral dl, integral E dot dl equal to minus integral double integral dou b by dou t dot n cap ds. So this is nothing but Maxwell's second equation in integral form. In a integral form, that is from the Faraday's law. Now we'll see the differential form. So by referring the Stokes theorem, integral E dot dl equal to integral del cross E dot n cap ds. The expression given by Stokes theorem is double integral E dot dl equal to integral del cross E dot n cap ds. So from equation 1 and 2, this left hand side is equal, so we can equate the term in the right hand side. Right? That is del cross E equal to minus dou b by dou t. By equating the right hand side term in equation 1 and 2, we got this. So this is nothing but Maxwell's second equation in differential form. Now we got the Maxwell's second equation in integral as well as differential form. Now we'll go to the third and fourth equation. So third and fourth equation from the Gauss law. What is Gauss law? According to Gauss law, flux coming out of a charged body is equal to the amount of charge enclosed. Pi equal to Q. Flux coming out of a charged body is equal to amount of charge enclosed in the circuit. Now we'll see what is pi, what is Q. So from displacement density is given as d equal to d pi by ds. And cross multiply this, d pi equal to d dot ds. So by pi equal to, by integrating on both sides, pi equal to double integral d dot ds. Right? Now we got the expression for pi from the displacement density. Similarly, by referring the volume charge density rho, dq by dv. Volume charge means charge per unit volume. You cross multiply this, dq equal to rho into dv. So by integrating on the both side, q equal to triple integral rho dot dv. Because of volume, we are having triple integral. Right? Now we got the expression for pi and q. So that can be substituted in the equation 1. Pi can be replaced by this term, q can be replaced by this term. Right? So the equation 1 now become double integral d dot ds, this one, equal to triple integral rho dot dv. Right? This is nothing but Maxwell's third equation in the electric field, in terms of electric field. Similarly, we have magnetic field available. So this is the Maxwell's third equation in electric field in integral form. The same thing from the divergence theorem. It can be written as del dot d equal to rho. By referring the previous equation from the divergence theorem, we can write like this. So this is nothing but Maxwell's third equation in electric field in a differential form. The third equation for electric field in differential form. This one is integral form, this one is differential form. Now we'll go to the fourth equation in magnetic field. Suppose in case of magnetic field, the surface integral of magnetic flux density B over a closed surface is S is 0. That is double integral B dot n cap ds equal to 0. That is given by the Gauss law in for a magnetic field. So this is nothing but Maxwell's fourth equation for magnetic field in integral form. So the same equation can be written as del dot B equal to 0. So this is nothing but Maxwell's fourth equation in of magnetic field in differential form. Right? Now we got the all four Maxwell's equation both in integral form and differential form. So in this video we discuss about the Maxwell's equation, right? 4 different equations available, both in integral form and differential forms are discussed. Thank you. Welcome viewers. In this video, we'll see the definition of the wave, uniform plane wave, followed by wave equation. First, we'll see the wave. The wave is nothing but, it is a physical phenomenon that occurs at one place at a given time, is reproduced at other places at later times. The time delay being proportional to the space separation from the first location, then the group of phenomena constitute a wave. The wave is nothing but, it is a produced at one place, available at one place, and reproduced at other places in several times in later time. That is nothing but a wave, right? It's available from one place to another place. In this, we have uniform plane wave is available. What is uniform plane wave? When it is, the wave is called a uniform plane wave. This is properties of the uniform plane wave. At every point in space, the electric field E and magnetic field H are perpendicular to each other and to the direction of the travel. If the electric field E and magnetic field H are perpendicular to each other, then it is a uniform plane wave, the first point. The field vary harmonically with time and same frequency everywhere in space, right? The field is varying harmonically with time and also same frequency in every space. Then also it is termed as a uniform plane wave. The third one is, each field has the same direction, magnitude and phase. The field having the same direction, magnitude and phase at every point in any phase perpendicular to the direction of the wave travel, right? If they having the same direction, same magnitude and phase in every point, that also termed as a uniform plane wave, right? Wave is nothing but occurs in one place, reproduced at other places. It can be termed as a uniform plane wave by satisfying these 3 properties. Now we'll go to the wave equation. The wave equation can be obtained from the Maxwell's equation. By referring from Maxwell's equation, we can get the wave equation for both electric field as well as magnetic field. So Maxwell's equation from Faraday's law is given as curl E equal to minus dou B by dou T. Right? We start from this equation, that is Maxwell equation from Faraday's law. Curl H equal to minus dou B by dou T. Now that the curl E can be written as dou B by dou T, that B is nothing but mu H. We can replace B with mu H, so that minus mu dou H by dou T. Now the B is replaced with mu H. Now take curl on both sides. We are going to take the curl on both sides. So that curl of curl E equal to curl of minus mu dou H by dou T. So that is nothing but del operator. Curl is nothing but del operator. Del cross E, that is equal to mu is constant, minus mu del cross dou H by dou T. Right? So we can take this is the equation number 1. Now Maxwell's equation from Ampere's law is given as curl H equal to J plus dou D by dou T. That is nothing but del cross H equal to sigma E plus epsilon dou E by dou T. So another form from the Ampere's law, Maxwell equation from Ampere's law, the del cross H equal to sigma E plus epsilon dou E by dou T. Now we'll take this equation number 2. Now we are going to differentiate the second equation. We are going to differentiate this equation. What is the differentiation? Del cross dou H by dou T. Differentiate. We are going to differentiate. Similarly, this side dou by dou T of sigma E plus epsilon dou E by dou T. So that del cross dou H by dou T equal to multiply inside. So sigma dou E by dou T plus epsilon dou square E by dou T square. Already here differentiation available, so it become dou square E by dou T square. Right, so we got this is the equation number 3. Now we are going to substitute this equation 3 in the first equation. We are going to replace this del cross dou H by dou T, we are going to replace in the equation 1. Right, so in this equation 1, so del cross E, that is the equation 1, that is equal to minus mu. Here we have the del cross dou H by dou T, this value we are going to replace. That is nothing but sigma dou E by dou T plus epsilon dou E square by dou T square. Right, now we are substituted the equation in equation 1, this value is substituted. Equation 3 is substituted in equation 1, we got this value. But from the identity, del cross E equal to del of del dot E minus del square E. So identity is available. And identity is, what is that identity? Del cross E equal to del of del dot E minus del square E. Now we'll see the other terms. Now from the identity, now we'll go to, since there is no net charge within the conductor, then the charge density rho equal to 0. Right, there is no net charge is available, so the charge density rho equal to 0. That means del dot D equal to 0, del dot E also 0. Therefore that identity we can write it as del cross E equal to minus del square E. The other terms become 0. These two terms become 0. So that can be written as minus del square E equal to minus mu sigma dou E by dou T plus epsilon dou E square by dou T square. So this del square E is written here. So the negative available on both the side, so we can write it as del square E equal to mu epsilon dou E by dou T plus mu sigma, this mu sigma dou E by dou T plus mu epsilon dou square E by dou T square. Now bring these two terms in the left hand side. So del square E minus, this term become minus while bringing this minus, mu sigma dou E by dou T minus mu epsilon dou E square by dou T square equal to 0. So this is the equation, this is the wave equation for electric field E. Having the electric field E is available. So this is the equation for the electric field. So similarly we can find the wave equation for magnetic field. The wave equation for magnetic field H also obtained in a similar manner. We start from the equation 2. Del cross H equal to sigma E plus epsilon dou E by dou T. Right, we start from equation 2. Now take curl on both the sides. Curl of del cross H equal to curl of sigma E plus epsilon dou E by dou T. So that is nothing but del cross H equal to del cross of sigma E plus epsilon dou E by dou T. Right, we start from the equation 2, that curl, take curl on both the sides, we got this expression. So this del cross H equal to sigma del cross E, we multiplied inside, sigma del cross E plus epsilon del cross dou E by dou T. This multiplied inside. You take this equation number 5. But from Maxwell's equation, from Faraday's law, what we need is magnetic field. So we are referring now Maxwell equation from Faraday's law. Curl of E equal to minus dou B by dou T. We already discussed curl of E equal to, that is del cross E equal to minus mu dou H by dou T. This B is replaced with mu H. B is nothing but mu H. You take this equation number 6. Right, now we got del cross E equal to minus mu dou H by dou T. That is, we are getting the relation between relating the electric field as well as magnetic field. Now differentiate this equation on both the side. So del cross dou E by dou T, this differentiation is minus mu, already differentiation available, so it becomes second order. Dou square H by dou T square. So del cross dou E by dou T equal to minus mu dou square H by dou T square. Now we'll go to the identity. What is the identity? Del cross H equal to del of del dot H minus del square H. And del dot H equal to 0. The identity, there is no charge, so this is 0. So it become del cross H equal to minus del square H. This term become 0. This is 0, so that this term become 0. We take this equation number 8, this equation number 7. Right? Now what we are going to do? We are going to substitute the equation 6, 7, 8 and in equation number 5. We already discussed what is the equation 6, what is 7, 8 and 5 also. We are going to substitute these three values in equation 5. So what we got? Minus del square H equal to sigma minus mu dou H by dou T plus epsilon of minus mu dou square H by dou T square. Right? So the negative available. So all the terms available with negative, so it become positive. Del square H equal to mu sigma dou H by dou T plus mu epsilon dou square H by dou T square. Now bring these two terms in the left hand side. So it become negative. Del square H minus mu sigma dou H by dou T minus mu epsilon dou square H by dou T square equal to 0. Right? So this take this equation number 9. Right? So this equation is called a wave equation in magnetic field. We already discussed the electric field. So this is a magnetic field is available, magnetic field intensity. This wave equation refers the wave equation in magnetic field. Now we got the wave equation for electric field as well as magnetic field. Now we'll see the wave equation for free space. So for the free space, what is the given? The free space, the conductivity of the medium is 0. Is sigma equal to 0. And there is no charge containing it. So rho equal to 0. So the free space means sigma equal to 0 and rho equal to 0. There is no conductivity, there is no charge available. So in the previous equation, the wave equation for electric field as well as magnetic field, we need to substitute sigma equal to 0 and rho equal to 0, so that we will get the wave equation for free space. Now what is the wave equation for electric field and magnetic field? We will see one by one. Therefore the wave equation in free space can be obtained from equation 4 and 9. So the wave equation for electric field is given as del square E minus sigma mu dou E by dou T minus mu epsilon dou square E by dou T square, that is equal to 0. So in this sigma equal to 0. There is no conductivity. Because of free space, the mu r value is 1. Epsilon r also 1. Only we go mu naught and epsilon naught. In the free space, this mu r value and epsilon r value equal to 1. So what will happen is the above equation become del square E minus, this term is not available, this is 0. Mu naught epsilon naught, due to free space mu r and mu epsilon r is 1, so that mu naught epsilon naught del square dou square E by dou T square equal to 0. So this is the equation for wave equation for free space for the electric field. Right? This term become 0 and these two term become mu naught and epsilon naught. Similarly, the wave equation for magnetic field is given as del square H minus mu epsilon mu sigma dou H by dou T minus mu epsilon dou square H by dou T square equal to 0. So this is the wave equation for magnetic field. In this the sigma is 0 and mu r and epsilon r also 1 due to free space. So what happened? This del square h minus mu naught epsilon naught del square h by del t square equal to 0. Dou square h by dou t square equal to 0. This term become 0. The sigma is not available. No conductivity 0. These two terms become mu naught and epsilon naught. So this is the wave equation for free space for a magnetic field. So now we got the wave equation for free space both in electric field as well as magnetic field. So in this video we discuss about the definition of the wave. Then properties of uniform plane wave. When we are termed as the wave is become the uniform plane wave by satisfying the properties. Then wave equation for electric field as well as magnetic field. Then wave equation for free space both for electric field and magnetic field. These topics are discussed. Thank you. Welcome viewers. In this video we will see the Poynting vector followed by the Poynting theorem derivation. First we will see the what is meant by intrinsic impedance or characteristics impedance. This given as a intrinsic impedance or characteristic impedance. It is a ratio of electric field to the magnetic field, E divided by H. The ratio of electric field by magnetic field is termed as a intrinsic impedance or characteristics impedance. And also it is a ratio of square root of permeability to permittivity of the medium, square root of mu by epsilon. Right? The another term is square root of mu by epsilon also it is given. The unit is ohms. Then we will see the Slipian vector. So it is a vector which is defined at every point such that its flux crossing out any volume is 0. It is termed as S. So del dot S equal to 0. Right? It is defined as a every point such that its flux crossing out of any volume is 0. So del dot S equal to 0. So S can be given as del cross V into H. What is V? V is the electric potential, H is magnetic field intensity. Right? So now we discuss the intrinsic impedance or characteristics impedance followed by Slipian vector. Now we'll go to the Poynting vector. What is Poynting vector? It is defined as a cross product of vectors E and H. S equal to E vector cross H vector. S vector equal to E vector cross H vector. What is A vector cross B vector? AB sin theta. So that E vector cross H vector equal to E dot H dot sin 90. Because the angle between E and H is 90 degree. So sin 90 is 1. So that S equal to E into H. Right? The Poynting vector S equal to electric field multiplied by magnetic field. Now we are going to substitute E equal to V by L. Electric field intensity is nothing but potential by length. Similarly, H equal to I divided by 2 pi R based on the Ampere's law. So this is a general formula. E equal to V by L, H equal to I by 2 pi R. Now we will substitute these two. E is replaced as V by L, H is replaced as I by 2 pi R. So while multiplying V into I divided by 2 pi RL. V into I divided by 2 pi RL. This V into I is nothing but power. Voltage into current. 2 pi RL is nothing but a area. Right? So power divided by area. So the Poynting vector gives power divided by area. That is Poynting vector gives power per unit area. So the Poynting vector will give the term power per unit area. Now we'll go to the pointing theorem. So the pointing theorem, first we'll start with pointing vector. Pointing vector is defined as cross product of vector E and H. So S vector equal to E vector cross H vector. Pointing theorem, we start with the pointing vector. So pointing vector is nothing but cross product of electric field intensity and magnetic field intensity. Take divergence on both the side. We are going to take the divergence on both the side. So divergence of S vector equal to divergence of E vector cross H vector. Right? The divergence is taken on both the side. But in general, divergence of U cross V, we can take two terms, two general terms. U cross V means, how will you write? Divergence of U cross V equal to V curl of U minus U curl of V. Right? First we need to write this V, then curl of U. Then you have to write V, then curl of V. So this is a general formula. So based on this general formula, we can write divergence of E vector cross H vector can be written as H curl of E minus E curl of H. By referring this general equation, general formula, we can write the divergence of E vector cross H vector can be written as H curl of E minus E curl of H. Right? So that we can write this. So divergence of S equal to H minus dou B by dou T. The curl E is nothing but minus dou B by dou T. Minus E, the curl H is nothing but J plus dou D by dou T. Right? So divergence of S, this divergence of S, this term is replaced by this formula. In this, curl H is minus dou B by dou T. This curl E is minus dou B by dou T. Curl H is J plus dou D by dou T. Now we'll substitute one more, B equal to mu H. We can replace this B with mu H. Similarly, D is epsilon E. There is a relation available, displacement density D equal to epsilon into E. So that this divergence of S equal to H into minus dou B by dou T. This B is replaced with mu H. Similarly, minus E of J plus dou by dou T of this D is replaced with epsilon E. Right? Now we can simplify this. Divergence of S equal to minus mu H. Right? Already one H is there, one mu is taken outside. So minus mu H dou H by dou T. We can multiply inside E into J, minus E into J, and multiply this with the term minus epsilon E dou E by dou T. This epsilon is taken outside. Right? Now we got three terms, minus mu H dou H by dou T, minus epsilon J, minus epsilon E dou E by dou T. I will go for the further simplification. For example, dou by dou T of half H square. How will you write the dou by dou T of half H square? That is, we are going to differentiate with respect to H. So 1 by 2, the differentiation of H square is 2H dou H by dou T. Right? So dou by dou T of 1 by 2 H square is nothing but 1 by 2 into the differentiation of H square is 2H dou H by dou T. These 2 got cancelled, H dou H by dou T. Right? So dou by dou T of half H square is equal to H dou H by dou T. See this term available, H dou H by dou T. This term can be replaced by this term, dou by dou T of half H square. We are going in a reverse order. This term we are going to replace with this. Similarly, dou by dou T of half E square, dou by dou T of half E square equal to 1 by 2. The differentiation of E square is 2E dou E by dou T. So the 2 got cancelled, E dou E by dou T. So this value E dou E by dou T can be replaced with dou by dou T of 1 by 2 E square. Right? So this value, this expression, this value and this value, we are going to replace with this term. So that divergence of S vector equal to minus mu This h dh by dt is nothing but now dou by dou t of half h square, this value. This value is replaced with this value minus ej epsilon e dou e by dou t. E dou e by dou t is replaced by dou by dou t of half e square. Now it is replaced. Now we'll go for the further simplification. Divergence of s equal to minus dou by dou t. This mu is brought inside. 1 by 2 mu h square minus ej. This epsilon is brought inside. Dou by dou t of half epsilon e square. Right? So this dou by dou t available in both the term that taken as common. Minus dou by dou t of half mu h square plus half epsilon e square minus ej. So these two terms, this minus dou by dou t is taken outside. Right? Now we'll go for the further simplification. So by rewriting we got minus ej equal to dou by dou t of half mu h square plus half epsilon e square plus divergence of s vector. Right? So this term is brought that side so that it become positive. We'll take this is the term 1. Minus ej will take it as term 1. This dou by dou t of half mu h square plus half epsilon e square will take it as second term. This divergence of s is the third term. So we'll analyze these three terms one by one. Right? So this is the first term, this is the second term, this is the third term. What is the first term Ej? Ej is nothing but this electric field intensity and current density. So the electric field intensity is V by L. Current density is I by A. Right? E is nothing but electric field intensity V by L. J is the current density I by A. So that VI divided by A into L. Voltage into current is nothing but power loss. Power or power loss. Area into length is nothing but volume. So this power loss can be written as energy loss divided by second. So energy is nothing but power into time. So energy divided by second will give the power divided by volume. So the Ej is nothing but energy loss per second per unit volume. It will give the value of what is the energy loss per second per volume. If it is plus Ej means energy loss per second per unit volume. Minus Ej means energy generated per second per unit volume. Right? This plus minus represent either energy loss or energy generated. Right. Then we'll go to the term 2, second term and third term. The second term is nothing but energy stored in electromagnetic field per unit volume second. Per unit volume and second. So the term 2 was giving energy stored in a electromagnetic field. The term 3 gives energy outflow per unit volume and second. Right? This gives the energy stored. Term 3 gives the energy outflow. So by combining these three, the Poynting theorem, the statement of Poynting theorem is nothing but, according to Poynting theorem, energy generated per unit volume per second, that is the first term, is the sum of energy stored in magnetic field per unit per second and energy crossed per unit volume and second. Right? The term 1 equal to sum of term 2 and term 3. That is the statement given by the Poynting. Right? So the energy generated is equal to the sum of energy stored and energy outflow. So this is the statement given by the Poynting theorem. Now the Poynting, this equation we can write it in a integral form. We got the Poynting theorem, the term 1 and 2 already we discussed. We can convert that into integral form. So multiply with volume on either side of the above equation. By referring the above equation, we are going to multiply with volume. So volume of dou by dou t of half mu h square plus half epsilon e square plus divergence of s equal to volume of minus Ej. So volume multiplied on both the side. So it become volume integral. So integral V is nothing but triple integral. Dou by dou t of half mu h square plus half epsilon e square into dv. Is that? volume integral. Similarly, this term integral V divergence of S into dV. Similarly, this term integral V volume integral minus E into J dot dV. So everything now converted into volume integral with respect to dV. So this is the integral form of the Poynting theorem, right? So this got the integral form. Previous one is the normal form, differential form. This will be the integral form. So in this video we discuss about the intrinsic impedance or characteristic impedance, Slipian vector, Poynting vector, followed by Poynting theorem, the proof of the Poynting theorem. Finally we got the integral form of the Poynting theorem. Thank you. Welcome viewers. In this video we'll see the polarization. The polarization is nothing but the uniform plane wave. The polarization of the uniform plane wave refers time varying behavior of the electric field strength vector at some fixed point in space. How the wave is behave with the time, that is nothing but polarization. Whether how it is varying with the given time, that is the polarization. Consider a uniform plane wave traveling in Z direction. We can refer the wave is traveling in the Z direction, E and H lying in the XY plane. Electric field and magnetic field is lying in the XY plane. So in this XYZ, the electric field intensity available in X plane, magnetic field intensity available in Y plane, and the plane wave is traveling in Z direction. Right. Based on that, we will go for the consideration. So in this, see the different types of the polarization. Suppose if EY is 0, only EX is alone available, then the wave is said to be polarized in X direction. Right? The EY is 0, only EX is available, mean that wave is polarized in X direction, only in X direction. Y direction is not available. Similarly, EH is 0, X is 0, Y only available. Then it is the wave is said to be polarized in Y direction, right? So in this only EX is available, so that polarized in X direction. Only EY is available, so polarized in Y direction. Other terms are 0. Suppose if both the EX and EY is available, then we'll see that if both EX and EY both are available, then it is called a linear polarization, right? So the EX is available in X axis, EY available in Y axis. This total E is nothing but sum of these two. From the diagram, this theta can be calculated as tan inverse EY by EX. So the magnitude of E is nothing but square root of EH square plus EY square, this vector sum. So in the first case only EX available, in the second case EY available, in the third one linear polarization both X and Y is available. So that linearly vary, it varies the waveform, right? We'll see the description. If both EX and EY are present and in phase or in phase, then the resultant electric field has a direction of angle tan inverse EY by EX, right? So in the third type, both EX and EY is available and also in the in phase. So the resultant electric field is having an angle of tan inverse EY by EX. If the direction of resultant vector is constant with the time, the wave is said to be linearly polarized, right? The direction of resultant vector should be a constant with time. Then it is said to be linearly polarized, right? Now we'll go to the next type. So the next type is the circular polarization. Here also EX and EY is available, having same magnitude and differ by 90 degree. The previous case in phase, but here differ by 90 degree, right? So EX available, EY also available, having the same magnitude and differ by 90 degree. Exactly 90 degree means the wave traveling is nothing but a circular polarization. Because of 90-degree, the wave will travel in a circular path. So this is Ex and Ey. Both are having same magnitude. The angle is 90-degree, so that the resultant will follow the circular path. Right? So the description is given. If Ex and Ey have the equal magnitude and a phase difference of pi by 2, then the locus of resultant electric field wave is a circle. Then the wave is said to be circularly polarized. Right? Ex and Ey available, both having same magnitude and differ by 90-degree. Then the locus will be circle. The waveform is said to be circularly polarized. We'll see the one special case in this, the next type, elliptical polarization. Right? So here also same, Ex and Ey available, but having different magnitude, A and B. See this, the Ex is lesser, Ey is higher. So for example, it is written like that. Both the magnitudes are not equal. In circular polarization, both are equal, and it's differ by 90-degree. That is same. The phase difference between A and B is 90-degree. Only thing is having different magnitude. So due to different magnitude, it follows the elliptical form, not a circular form. Having the same magnitude mean we'll get circular polarization. So due to different magnitude, we are getting the elliptical polarization. So the description is available. Ex and Ey have different amplitude and phase difference of pi by 2. The locus of the resultant E is ellipse, and the wave is said to be elliptically polarized. Right? So in this we discuss the 5 types. That is, only Ex available means polarized in x direction. Only Ey is available means polarized in y direction. If both are available and is varying with the time, means it is linear polarized. If both are available with the same magnitude and 90-degree, means circular polarization. If both are available with different magnitude and 90-degree, means elliptical polarization. So these 5 types we discussed in this video. Thank you.